Now we determine the electric potential due to a point charge. We already saw that the potential energy U of a test charge QP at a point P in an electric field due to a point charge Q is given by 1 over 4 pi times epsilon naught, times the product of the point charges Q and QP over the distance are between the point charges. Since the potential of the electric field at the point P is defined by the ratio of the potential energy of the test charge QP to the amount of the charge, we can write the potential phi due to a point charge Q at a point P as 1 over 4 pi times epsilon naught, times the amount Q of the point charge divided by the distance are between the point P and the point charge Q. This formula shows that the potential due to a static point charge is directly proportional to the amount of charge producing the electric field, and inversely proportional to the distance from the point charge. In the case of the electric field strength E due to a point charge, we saw that the magnitude of E is inversely proportional to the square of the distance from the point charge. As a result, it drops off faster than the potential as we approach infinity. Because of spherical symmetry, the potential, similarly to the magnitude of the electric field strength, is constant over the spheres with the center at the point charge producing the field. Therefore, these spheres are called equipotential surfaces of the electric field. By generalizing this result, we can determine the electric potential due to a system of point charges. Let us suppose that the electric field is produced by a system of point charges Q1, Q2, ellipsis Qn, where the distances of the individual point charges from a reference point O are r1, r2, ellipsis, rn. We can determine the work done by the electrostatic field while a test charge QP is brought from the point P1 to the point P2 in the field due to the system of charges if we apply the principle of superposition for work. The latter states that the total work done by the electrostatic field due to a system of point charges is equal to the algebraic sum of the works done by the electrostatic fields due to the individual point charges in the system. We already determined the work done by the electrostatic field due to a single point charge, and we found that it is equal to 1 over 4 pi times epsilon naught, times the difference between the product of Qi and Qp over R sub I1 and the product of Qi and Qp over R sub I2. Here Qi denotes the ith point charge in the system, and R sub I1 and R sub I2 are the distances of the point charge Qi from the points P1 and P2, respectively. Then the work done by the electric field due to the system of point charges is given by 1 over 4 pi times epsilon naught, times the sum of the differences between the product of Qi and Qp over R sub I1 and the product of Qi and Qp over R sub I2 for I from 1 to n. By removing the parentheses we obtain two terms, and if we compare them with the expression obtained for the difference in the potential energy of the test charge Qp at the points P1 and P2 in an electrostatic field due to an individual point charge, we can conclude that the potential energy U of the test charge Qp at a given point P is equal to 1 over 4 pi times epsilon naught, times the sum of Qi times Qp over the distance or I between the point charge Qi and Qp. As a result, the potential phi at a given point P in the electric field due to the system of static point charges Q1, Q2, ellipsis, Qn is given by 1 over 4 pi times epsilon naught, times the sum of the point charge Qi over the distance or I between the point charge Qi and the point P. This formula shows that the potential due to the system of point charges is the algebraic sum of the potentials due to the individual point charges. Based on this result, we can determine the electric potential due to a dipole in the region far from it. We will compute the potential phi at the point P at the distance r from the midpoint O of the dipole, which is much greater than the distance d between the point charges minus q and plus q. Here the electric dipole moment P is given by the product of the charge q and the vector d pointing from the negative charge to the positive one. The principle of superposition tells us that the electric potential phi at the point P is equal to the sum of the electric potentials due to the point charges plus q and minus q at the same point. That is, phi is given by 1 over 4 pi epsilon naught, times the difference between q over r sub plus and q over r sub minus. Here r sub plus and r sub minus are the distances of the point charges plus q and minus q from the point P. The terms in the parentheses can be written as q times the difference between r sub minus and r sub plus, divided by the product of r sub plus and r sub minus. If the angle between the vector d and the vector r pointing from the midpoint O to the point P is denoted by theta, we can apply the cosine theorem to express the squares of r sub plus and r sub minus as the square of r, plus the square of d divided by 2, minus or plus 2 times d divided by 2 times or times cosine theta. By completing the square, we write the right-hand side of the equation as the square of r minus or plus d over 2 times cosine theta, plus the square of d over 2, minus the square of d over 2 times the square of cosine theta. Since d over 2 is much smaller than r, we can drop the second and the third terms in the right-hand side, and approximate the distances r sub plus and r sub minus as r minus or plus d over 2 times cosine theta. Here the second term can be written as the scalar product of the vector d over 2 and the unit vector er pointing in the direction of the vector r. Therefore, the difference between r sub minus and r sub plus can be approximated by 2 times the scalar product of the vector d over 2 and the unit vector er, that is the vector r divided by its length. As a result, the difference between r sub minus and r sub plus is given by the scalar product of the vectors d and er. The product of r sub plus and r sub minus can also be approximated by r squared minus the square of the dot product of d over 2 and er. Since the second term is negligible compared to the first one, it can be dropped from the right-hand side. If we substitute this approximations into the ratio of q times the difference between r sub minus and r sub plus to the product of r sub plus and r sub minus, we obtain q times the scalar product of the vectors d and er over r squared, where q times d is equal to the dipole moment p. As a result, the electric potential phi due to a dipole with the electric dipole moment p at the distance r can be written as 1 over 4 pi epsilon naught, times the ratio of the scalar product of the vector p over r squared and the position vector r divided by its length r. Since the scalar product of the dipole moment p and the unit vector er is equal to the magnitude of the vector p times the cosine of the angle theta between the dipole moment p and the position vector r, the electric potential can also be written as 1 over 4 pi times epsilon naught, times the ratio of p times cosine theta to r squared. These equations show that the potential far from the dipole is directly proportional to the magnitude of the electric dipole moment p and inversely proportional to the square of the distance. We can also see that the potential has a maximum along the axis of the dipole, and vanishes in the equatorial plane of the dipole as we change the position of p while keeping the distance r constant. For a given direction pointing from the midpoint to the point p, the potential varies with the inverse square law, as opposed to the potential due to a point charge which is inversely proportional to the distance. Then we conclude that the potential due to a dipole drops off faster than the potential due to a point charge as we approach infinity. We already determined the potential due to a system of point charges in the general case. Now we derive a formula for the potential at large distance from the system, as we did in the case of the dipole. Let us consider the system of point charges q1, q2, ellipsis, qn, where d is the maximum distance between 2 point charges in the system. In other words, a sphere of radius d can enclose the whole system of point charges. We will compute the electric potential at the point P given by the position vector r pointing from a reference point O in the sphere, for example at its center. Since the point P is far from the system, the radius d is much smaller than the distance r, that is the length of the position vector r. Letter I denote the position vectors pointing from the reference point to the individual point charges qi. Then the electric potential far from the system of point charges is determined by the potentials due to each point charge qi at the distance r minus ri from the point P. If we apply the principle of superposition, we can write the potential phi at the point P as 1 over 4 pi epsilon naught, times the sum of the ratio of the charge qi to the magnitude of the difference between the position vectors r and ri from I equals 1 to n. Here 1 over the magnitude of the difference between the position vectors r and ri is given by 1 over the square root of r squared, minus 2 times the scalar product of r and ri, plus ri squared. By introducing the notation x for minus 2 times the scalar product of r and ri over r squared, plus the square of ri over r, we can write this fraction as 1 over r times the square root of 1 plus x. Since the distance ri for each point charge qi is much smaller than the distance r, the magnitude of x is much smaller than 1. Then we can apply the generalized binomial expansion of the function 1 plus x over alpha, where alpha is an arbitrary number. The expansion of this function around 0 is given by the sum of the ratio of alpha factorial to the product of k factorial and k minus alpha factorial, times x to k with the index k running from 1 to infinity. The infinite sum is equal to 1, plus alpha over 1 factorial times x, plus alpha times alpha minus 1 over 2 factorial times x squared and so on. If alpha is equal to minus 1 over 2, then we can expand 1 over the square root of 1 plus x as 1, minus 1 over 2 times x, plus 3 over 8 times x squared and so on. This formula helps us to approximate 1 over the magnitude of the difference between the position vectors r and ri in first order as 1 over r, times 1 plus the scalar product of the position vector ri and the unit vector er pointing in the direction of r, divided by r. In the first order approximation we dropped all the terms which contain ri raised to the power greater than 1. By substituting this approximation into the equation of phi, we can write the electric potential at the point P due to the system of point charges Q1, Q2, ellipsis, Qn is 1 over 4 pi times epsilon naught, times the sum of the charge Qi divided by r from I equals to 1 to n, plus 1 over 4 pi times epsilon naught, times the sum of the charge Qi times the scalar product of the position vector Ri and the unit vector Er divided by r squared from I equals to 1 to n. We note that the sum of the charges Qi gives the total charge of the system of point charges, whereas the sum of Qi times Ri can be interpreted as the electric dipole moment of the whole system. The formula derived for the electric potential far from a system of point charges is only a first-order approximation of the electric field due to the system, and it is called dipole approximation for the following reasons. If the total charge of the system does not vanish, then the first term in the formula becomes dominant in the far field approximation of the electric potential, whereas the second term proportional to the inverse square of the distance has a negligible contribution to the potential at large distance. In the calculation of the potential at a given point, the system of point charges with negligible mutual distances compared to their distances from the point can be approximated by a single point charge uniting the total charge of the system. In the case of an electrically neutral system of point charges, the sum of the charges in the system vanishes and the first term is identically zero. However, the second term generally does not vanish and determines the potential far from the system. As a result, the electric potential due to an electrically neutral system of point charges can be approximated at large distance by a potential due to a dipole with the electric dipole moment of the system. Therefore, such a description is called the dipole approximation of the potential due to the given system of point charges. In fact, the dipole approximation of electric potential can be applied in many cases. For example, a water molecule consists of 2 hydrogen atoms and 1 oxygen atom, where the angle of the bonds between the hydrogen atoms and the oxygen atom is about 104 degrees. Because oxygen is more electronegative than hydrogen, the oxygen atom attracts electrons more and keeps them away from the 2 hydrogen atoms in the molecular bonds. As a result, each hydrogen atom has a positive partial charge Q, while the oxygen atom has the negative charge -2 times Q, and the molecule is electrically neutral at large distance. At the same time, the vector sum of the electric dipole moments pointing from the oxygen atom to the 2 hydrogen atoms gives a non-vanishing electric dipole moment. Therefore, the water molecule is a polar molecule, and its electric potential can be described by dipole approximation. As a result, dipole-dipole interactions can be observed between polar molecules which align so that the positive end of one of the molecules interacts with the negative end of the other one. Since we talk about an interaction between molecules, we also call it intermolecular attraction, and we can describe it by the dipole approximation of the potentials of the individual molecules attracting each other. Besides dipoles, another important system of point charges is a quadrupole formed by 2 dipoles with opposite orientations. In the figures we show 2 types of quadrupoles with the electric dipole moments lying on the same or parallel lines, where both the total electric charge and the dipole moment of the system are zero. However, the electric potential due to a quadrupole does not vanish, which means that higher order terms must also be taken into account in the Taylor expansion applied in the approximation of the potential. When we expanded the reciprocal of the distances between the individual point charges in the system and the point P where the potential was determined, we introduced the shorthand notation x for -2 times the scalar product of the position vector r of the point P and the position vector Ri of each point charge Qi divided by r squared, plus the square of the ratio of Ri to r. We also provided the Taylor expansion of 1 over the square root of 1 plus x as 1 minus 1 over 2 times x, plus 3 over 8 times x squared and so on. In the dipole expansion of the potential we cut the sum of the infinite series after the terms of first order in Ri, but in the quadruple expansion we include the second order terms in the approximation. As a result, the reciprocal of the distance between the point P and the point charge Qi can be approximated as 1 over r times the quantity of 1 plus the scalar product of Ri and the unit vector Er divided by r, minus 1 over 2 times the square of Ri over r, plus 3 over 2 times the square of the scalar product of Ri and the unit vector Er divided by r. Here we drop the terms where I is raised to the power greater than 2. By substituting this equation into the general form of the electric potential phi due to a system of n-point charges, we obtain its quadrupole expansion. Then phi is equal to 1 over 4 pi epsilon naught, times the sum of Qi over r, plus Qi times Ri times Er over r squared, plus Qi times the difference between the square of the scalar product of Ri and Ei, and Ri squared over 2 times the cube of r, for I equals to 1 to n. The first two terms in the curly brackets are simply the monopole and the dipole terms in the dipole expansion of the potential, whereas the last one is the quadrupole term of the higher order expansion. These three terms are inversely proportional to the distance r, the square of the distance r and the cube of the distance r, respectively. Therefore the quadrupole term has a faster falloff far from the system of point charges than the first two terms. However, if the monopole and the dipole terms vanish as in the case of quadrupoles, then the potential is determined by the quadrupole term. An example for the first type of quadrupoles is the carbon dioxide molecule, where the angle of the bonds between of carbon and oxygen atoms is 180 degrees. Here the oxygen atoms have positive partial charges Q and the carbon atom has the charge 2 times minus Q. In fact, we can also include terms of higher order than 2 in the expansion of the electric potential due to a system of point charges. We can call point charges or monopoles zeroth order multipoles. Similarly, dipoles are also known as first-order multipoles, quadrupoles as second-order multipoles, octupoles as third-order multipoles and so on. Now we determine the electric potential due to a continuous distribution of electric charge. In order to describe such a charge distribution, we introduced electric charge density. In the case of a given amount of charge Q distributed along a curve calligraphic C, we talked about the linear electric charge density lambda, where the product of lambda and a line element ds along the curve gives the infinitesimal charge dq of that line element. For a given amount of charge Q distributed over a surface calligraphic S, the product of the surface charge density sigma and the area element d capital S gives the infinitesimal charge dq of the surface element. Similarly, for the spatial charge density ρ describing the distribution of the electric charge Q in a given volume calligraphic V, the infinitesimal charge dq in the volume element dV is given by ρ times dV. We can determine the electric potential due to a continuous distribution of electric charge along the curve, over the surface or in the volume, if we approximate the continuous distribution of the charge as a system of point charges distributed along the curve, over the surface or in the volume. In the case of the electric charge distributed along the curve calligraphic C, we approximate the curve with n line segments, where delta S1, delta S2, ellipsis, delta Sn are the lengths of the line segments. If the length of each line segment is much smaller than the length of the curve, then we can also approximate the electric charge Q distributed along each line segment I with the point charge Qi at the middle point of the line segment. As a result, we obtain a system of point charges Q1, Q2, ellipsis, Qn along the line segments approximating the curve calligraphic C. We can follow the same procedure in the case of the continuous distribution of electric charge over the surface calligraphic S. We construct an approximation of the surface with n flat surface elements delta capital S1, delta capital S2, ellipsis, delta capital Sn, where the area of each surface element is much smaller than the total area of the surface. We can approximate the continuous distribution of electric charge Q over the surface with the system of point charges Q1, Q2, ellipsis, Qn at the midpoint of each surface element, where the electric potential is the sum of the potentials due to the individual point charges in the system. We break up the volume calligraphic V into n volume elements delta V1, delta V2, ellipsis, delta Vn as well. Here the volume of each volume element is much smaller than the volume calligraphic V. Then we approximate the continuous distribution of the electric charge Q in the volume calligraphic V with the system of point charges Q1, Q2, ellipsis, Qn at the midpoint of each volume element. In these three cases the electric potential at a given point described by the position vector pointing from an arbitrary reference point is given by the sum of the potentials at the given point due to the individual point charges of the system. By refining the approximation of the curve calligraphic C with the series of line segments such that the length of each segment tends to 0 while their number n goes to infinity, the point charges Qi become the infinitesimal charge dq expressed as lambda times the infinitesimal arc length ds, and we can replace the sum of the potentials due to the individual point charges with a line integral along the curve. In the limit, the electric potential phi at the position are due to the continuous distribution of electric charge described by the linear charge density lambda along the curve calligraphic C is equal to 1 over 4 pi times epsilon naught, times the line integral of the linear charge density lambda divided by the length of the position vector are along the curve calligraphic C. Similarly, the area of each surface element delta capital Si tends to 0 if the number n of the surface elements goes to infinity, and the point charges Qi become the infinitesimal charge dq given by sigma times the infinitesimal surface element d capital S. Therefore the sum of the potentials becomes a surface integral. As a result, the electric potential phi at the position are due to the continuous distribution of electric charge given by the surface charge density sigma over the surface calligraphic S is equal to 1 over 4 pi times epsilon naught, times the surface integral of the surface charge density sigma divided by the length of the position vector r over the surface calligraphic S. If we refine the approximation in the third case such that the volume of the individual volume elements delta Vi tends to 0 while the number n of the volume elements goes to infinity, the point charges Qi become the infinitesimal charge dQ given by ρ times the infinitesimal volume element dV, and the sum of the potentials becomes a volume integral. In the limit, the electric potential phi at the position are due to the continuous distribution of electric charge described by the charge density ρ in the volume calligraphic V is equal to 1 over 4 pi times epsilon naught, times the volume integral of the charge density ρ divided by the length of the position vector r over the volume calligraphic V.